In 4.2, we start to look at different types of functions, and they have you graph all three of these. You can check the packet for more accurate representations, but if this was going to be f of x, it looks like a slope of 1 going through -1, so something like that. If we look at g of x, it's going to be slope of -1/2, or +1/2 rather, and going through -1/2, so it's a little bit flatter, but something like that. This guy looks a little bit different, and it kind of looks like a line, but you'll notice when x is 2, there's actually a little gap there. We call that a removable discontinuity. So some interesting things happen when we put a polynomial down in the bottom, like x minus 2. But they're going to ask in 4.2, how can you graph a rational function? We want to be able to do this kind of by sketching it without using Desmos. For example 1, they ask how can you use long division, which we didn't really talk too much about long division, so I'm actually going to show you how you can use synthetic division. So in the previous chapter, when we used synthetic division, we always looked at what the denominator 0 was. If this was going to be a factor, we needed to put in what would make it be 0. So we put in the 3. The 4x is what we're starting with, or our dividend. So we're going to have our 4 here, and there was nothing else. So I just added a 0 to put a spot for the remainder. Drop down the 4, multiply, give me 12. So I have this 12 left over. So our answer is just a 4 with a remainder of 12. It's not even a linear function, it's just a constant. Well, what this actually means is it could look like the function of our new function g of x could be rewritten as 4 plus 12, because that was your remainder, remember, over the divisor of x minus 3. You can always put that divisor of x minus 3 back under the remainder. Well, this actually looks a lot more like the ones we just did in 4.1. This 4 will shift the graph up 4. The parent function, if you will, remember. This 3, the minus 3, will move it to the right 3. And this 12 will push it out from the x-axis, just kind of push it out, kind of like a dilation, if you will, back in the day. So we could sketch that, and you sure can when you look at Desmos. But something to remember how our original x and y axis had the horizontal asymptote and the vertical asymptote. That was on the parent function of y equals 1 over x, that inverse function. Well, with this new graph, we can move our asymptotes by knowing we're going to be moving it up 4. So this horizontal asymptote will be here at y equals 4. And our vertical asymptote moving to the right 3 will be at x equals 3. So that's a good place to start. When you can move your asymptotes by the translations, that will help. Now, of course, we know the general shape. I'd recommending just plugging in a few numbers or checking on Desmos. It's going to kind of look like this, but it's going to be pushed out a little bit more from that 0, 0 because of that 12 up top. So example 1 in 4.2, part A is not bad. Part B is a little funky. You could sure check the packet, but I'm going to try the try it under the try it from example 1. I have the 1x here because of that 1x. Because the 0 of this is x minus, or the factor is x minus 6, I'm going to put the 6 in here. And I'm going to put a 0 here because there's no constant term. Drop down the 1, multiply by 6, throw it out into there, and we have our 6. So my function f of x could be rewritten as a 1 plus 6 over x minus 6. That would mean that this 1, remember the parent function, the parent inverse function is 1 over x. Well, now we have a 6 over x, so that's going to push it away from the origin. Okay, just push it out a little bit instead of at 0, 0 or whatever. This 1 is going to move it up 1, and this minus 6 is going to move it to the right plus 6. So remember how our original parent function, I'm going to draw this in pink for the parent function, it was a vertical asymptote on the y-axis and the horizontal asymptote here. Because of these shifters that I have, this up 1 plus this plus 1 here, that's going to move my horizontal asymptote up 1. So at y equals 1 is my horizontal asymptote. And it's going to move my vertical asymptote over 6 to the right. And so I'll have a vertical asymptote now at 6. And again, to get these points to actually graph it, remember the look of the inverse function is kind of like this a little bit. It's going to be that same look, and we're almost out of room on our graph here. I just recommend testing some points. Plug in 8 for say, or plug in, so if we put in 8 in here, 8 minus 6 is 2, 6 divided by 2 is 3, and 1 plus 3 is 4. So actually the 8, 4 would be my point. I'm going to just kind of give you a general look here. Again, you can check on Desmos. We'll know that it's not going to be real close like the original parent was. It's going to push out just a little bit, but we do know where the asymptotes are from those transformations that we created. So a couple of vocabulary or concepts to look at. A rational expression is just a polynomial over a polynomial. Okay, you've seen lots of them already. This right here is a rational expression. But when you put an equation or an equal sign into it, it becomes a function. Okay, so a rational is just like a ratio or a fraction of two polynomial expressions. When you get the function word in there, that means you're going to have that equal. Do note that the bottom cannot just be 0. Your denominator is not just the function 0, which we haven't really ever seen one of those anyhow. When we look at example 2, they want to know how do you find vertical and horizontal asymptotes, especially without graphing. So I've taken the liberty of, on the denominator of this function, factoring it. So this x squared plus 7x plus 12, I factored it. You thought factoring went away. By all means, it is alive and well. You still need to be able to factor as efficiently as possible. So that's not what you're getting stumped up over. But if we do that and we rewrote the equation as 3x minus 2 over x plus 3 times x plus 4, we should be careful to note what values we cannot plug in for x, because if we do, it'll make the denominator go to 0. And so those are zeros of the denominator at -3 or -4. So that means our vertical asymptotes are at x equals -3 and x equals -4. Let's repeat that. By factoring, you can see zeros easier. And if you know a 0 is going to happen in the denominator, even like up here, you can't divide by 0. The graph will be undefined there. So on that asymptote, we have a vertical one at x equals -3 and x equals -4, which of course also restricts your domain. They don't ask about domain here, but your domain would be all real numbers, except for x is -3 and x is -4. Now when it comes to horizontal asymptotes, the line that goes across that it can't cross normally, there's a little bit of a cheat here. We talked in example 1 with that weird synthetic division about how you could notice the parent function being translated, up or down, and that would move your horizontal asymptote. That's still fair game. But there's actually a cool cheat here. If your degree of the numerator is less than the degree of the denominator, so look right here, the degree of the numerator is 1 and the degree of the denominator is 2. So since 1 is less than 2, you will always have a horizontal asymptote at 0, y equals 0. If, in case 2, the degree of your numerator is bigger than the degree of your denominator, so right here, degree of the numerator bigger than the degree of the denominator, it's always going to be that your horizontal asymptote is at infinity. Basically, the graph's going to right off up to infinity on the end behaviors. For case 3, if your degrees are the same, look at x squared and 3x squared, then your horizontal asymptote is at y equals coefficients of the highest powers. What's that mean, you say? Okay, let me change back to my pen here. We would say for this example, see there's a 1 here and a 3 here. Our horizontal asymptote would be at y equals 1/3. So if I want to try B, I can use this little shortcut here, and I can say, look at the highest power of both the numerator and the denominator. The numerator is smaller, it has a 1 power, than the denominator. The denominator is 2. When your numerator is less than the denominator, our horizontal asymptote is at y equals 0. Simple as that. I'd put this in your packet and memorize it. So, for example, on the try it here, it's always recommended that you factor the denominator to help you get those vertical asymptotes. We'd have x minus 4 and x plus 2. That means if I would put a 4 in here, that'd be a bad thing, or a -2. So my vertical asymptotes are at x equals 4 and x equals -2. My horizontal asymptotes, remember, those are found by looking at the highest powers. They match. The degrees do, that is. So my horizontal asymptote is at y equals the coefficients. There's a 2 and a 1. So I don't have to write 2 over 1. I can just write 2. If you want to write 2 over 1, that's fine. But because the powers were even, or the same, that is, then you use the coefficients for your horizontal asymptote. One little habits of mind down here, it says, where would there be an equation where the horizontal asymptote is at -2? You could make anything you want. You could say -2 x to the 9th plus 7x squared minus 3 over x to the 9th plus 5. Okay? As long as these have -2 over 1 and the powers are the same, you'd find your horizontal asymptote to be there at -2. On example 3, a little bit trickier, you can't really factor this denominator. So for a vertical asymptote, if it's not a factoring one, just decide what would make it be 0. If you set it equal to 0, you'd have 3x equals 4. So if you divide by 3, we'd say at x equals 4/3, we would have 4/3 have a vertical asymptote. So that'd be like 1 1/3, go like right here. And I like to label, in case someone didn't know exactly what decimal I was drawing that line at. My horizontal asymptote comes from looking at the highest degrees of both the numerator and the denominator. Since their degrees are both 1, we know that horizontal asymptote is at y equals 2 over 3. So on my graph, I'd go to about 2/3 on the y-axis and draw in my horizontal asymptote. Now, for test x values, you might want to try a 2, you might want to try a 3, you might want to try a 0. Plug in some numbers into this equation, or check them on Desmos, and you get a general idea of what that graph might look like for that inverse function. Now, I skipped over example 3's triads, but that same thing we just did on the example 3 would be applied to all of those triads in example 3. Example 4 is just a real-world application problem. They actually give you this equation built into the picture, so you already have one there. The only thing you could be a little careful about is you might want to write it as -p plus 100. They did write it a little bit different, but always have your p's or your highest power to make standard form there. And they want to know, what percent of the pollutant can be removed for 78.3 million. The first thing we want to notice is that if you put 100 in there, that would be a problem. So we're definitely only going to have, we're going to have a vertical asymptote at p equals 100 if we're thinking graphically. Now what that means is our percents, okay, must be between 0 and 100, which makes sense because you don't really go over 100%. But with this one, they want to know what percent can be removed. P is 4%. For 78.3 million. If you had something like this, you'd want to sketch this blue side of the graph. I'd do it on Desmos for now, and sketch this, or write y equals 78.3 and find where they meet. If you use that graph, they do meet on Desmos when p is approximately 90. So that would tell us about 90% could be removed for $78.3 million. And finally, on example 5, it's basically doing that same thing. Again, I always recommend factoring your denominator, so x plus 5 and x minus 3. Your vertical asymptotes come from what would make your denominator be 0, so 3 would be bad, and -5 would be bad. Your horizontal asymptotes come from the highest powers, so I'd have y equals 4 as my horizontal asymptote. I could draw that in here, and draw my -5 and my +3, a little sketchy here. That gets a little crazy. I would definitely recommend testing some values in between each of these spots. So again, use Desmos to look at that. We're just generally going to want you to find these key asymptotes on your own, and then you can use some testing points or Desmos to finish the graph.